Well, good morning. My name is John Rogers. I'm with the Division of Oil, Gas, and Mining, and I'd like to welcome to our January Uinta Basin Collaborative meeting. Last year at this time, we were in Duchesne, and in the back of our minds, maybe some of us had heard of this virus, but never really gave it much thought at that time. So we had our meeting, it was normal, but then when April came around, we realized this was going to change things, so it was canceled. And in fact, three canceled. One, we were snowed in and fogged in. Another was due to US 40 being closed due to fire and the virus. So hopefully this is the last and we'll be together soon again. As far as the division, we've seen prices rebound into the low 50s, which has stabilized production. So things have taken a turn up since midsummer. So we like that. And we also see that prices have rebound based on the vaccine. So hopefully we'll see a change in the coronavirus and demand will go up and we'll see a turn in the industry. Today we're going to be talking about produced water. And water and energy have a very close tie to one another. You need a lot of water to produce energy. And then when we produce oil and gas, there's a lot of produced water that has come along with that. And so it's a situation that we have to deal with. It's common, and it's a problem that is very real, both economically and environmentally, how to handle this product. So today we're going to be hearing from two people that are very involved with the environmental side and the production of produced water and the best way to handle it. And so I'll turn the time over to John Baza, the Director of the Division of Oil, Gas, and Mining, to introduce our two speakers.
Thanks, John. And as an introduction to the subject today, I wanted to say that the Division of Oil, Gas, and Mining is a principal regulator for the upstream oil and gas business, meaning that once the oil or gas leaves the well site, lease, or producing unit, we kind of shed our regulatory control over that. But we also collaborate with other agencies of the state, air quality, water quality, and we are very concerned on the upstream side that we're mining the store and minimizing the impacts to both air and water from the upstream petroleum operations. Over the last year or so, I've been trying to educate myself on what those impacts are. I think that the division in our job, we tend to rely on fact and science, and I'm very concerned about making sure that we're using good science as we apply our rules and regulate the oil and gas industry. And you've probably heard the same thing I've heard over the years, that produced water in evaporative pits can have an effect on the ozone situation in the Uinta Basin, mainly because of the ozone precursors that come off those pits. The presenters we have today, and I'll introduce each of them in their turn. The first one is Mark Mansfield, and he's with Utah State University. And he's going to talk about how these produced water evaporation ponds do contribute to air quality and emissions out in the basin. So they've done a study of the evaporation ponds in Utah and Wyoming. So let me take a minute and introduce Mark, and I'll turn the time over to him. And then when it's the next presenter's turn, I'll introduce that subject as well. But Mark is a native of the Uinta Basin. He's got a bachelor's degree from the University of Utah and a PhD from Dartmouth. He's worked as a professor in chemistry for related fields in Maryland, Michigan, and New Jersey. He joined the Bingham Research Center at USU in Vernal when it was dedicated in 2010. He's been involved in air quality research ever since then. So we'll go ahead and turn the time over to Mark and allow you to present your information, Mark. Thank you so much.
Okay, yeah, thanks for the opportunity. Can everyone hear me?
Good.
Okay, let's see. Okay, I hope you can see this presentation. It's a PowerPoint presentation.
Yes, we're seeing the PowerPoint window right now, Mark.
Okay. Okay, yeah, thanks. Like I said, thanks for the opportunity to speak today and talk about our work. I'm representing myself and Seth Lyman, who's also on the call. We're going to talk about research that we've done over the past few years on the produced water evaporation ponds. I want to start out. Well, I'm sure as most of you know, produced water is water that comes up when oil or natural gas are produced. And sometimes, often barrel for barrel, wells produce more water than oil. I'm sure you also realize that that's not pure water that comes up out of the ground. Often it's saline. These waters, in some cases, have been down there. Well, they were once ancient oceans, or they've picked up salt from the formations that they're in. So produced water is often salty. These waters have been in contact with petroleum formations for millions of years. We all know that water and oil don't mix, but that's not true. They do slightly. So even after the produced water goes through the separator, it contains dissolved or suspended hydrocarbons. And that's basically the problem. The question is, how many of those hydrocarbons from the produced water eventually get into the atmosphere and contribute to air quality problems? The produced water also often contains methanol. That's not coming from deep underground, but it's present there because methanol is used as an antifreeze in natural gas wells and lines. And it also contains just very small amounts of other oxygenated compounds like carbon dioxide. These compounds have been underground for millions of years where there's no oxygen to speak of. So at least when the produced water comes out at the beginning, there are only trace amounts of oxygenated compounds. In the Uinta Basin, about something like 95% of all of the produced water that comes out of the ground gets re-injected. We put it back where it came from. But then about the remainder gets dumped into produced water evaporation ponds. In other words, we just dispose of it by evaporation. So it's trucked to the ponds and dumped in. Here are three photos showing several different ponds to give you an idea of what they look like.
Yeah. I'm sorry to cut in. It seems like we're not seeing your presentation change slides.
Okay. What are you seeing now?
We're just seeing your title slide. Could we have you hit the play from start button on the top left and make the home button?
Yeah, that's what I hit.
Do you have multiple screens?
Yeah. You see it now?
Mark, yes, we see the second one now.
Okay, well,
We're going to have you possibly switch your presentation to the screen that has the full PowerPoint on it. We're seeing what you're seeing on your screen. Yeah, like we're editing the PowerPoint still.
no.
Mark, can you go to the lower right and see the presentation view next to the slider in the lower right part of your PowerPoint screen? It looks like a screenshot. Click on that and see if you get the presentation.
Okay.
No, you didn't get it. It's not. It's in the lower right portion of your screen there.
That button.
Right. See the button next to the slider on the left?
Yeah.
Click that. See what we get.
Well, that's going to give the same thing. What do you see now?
It did. It did. And yeah, we're saying the same thing. I think what you're going to have to do is just point to each slide and click on it with your mouse, and they'll move as you hit one at a time.
Yeah. So you can see it now, right? Come on. Now this is slide number 2 where I'm talking about what's in the water. And slide number 3, can you see that?
Yes, we certainly can.
Okay. Yeah, sorry for the confusion. These things never work well because I have several monitors and I can never figure out which one to get it to display. So yeah, there are 3 shots of some of the ponds. We've actually worked on 3 separate projects studying the evaporation ponds, going back now for quite a few years. One project was for RIPSI Research Partnership to secure energy for America. The other 2 projects we performed for the Wyoming Air Quality Division in partnership with a consulting firm called GSI. We made measurements at 4 different sites in Wyoming and also many sites in the Uinta Basin, although we can't disclose the locations we visited and made measurements in the Uinta Basin. The basic measurements that we made, there are 2 important quantities. One is what we'll call the emission flux. So that's you have compound X in the pond. The flux is the milligrams per square meter per hour of that compound coming out of the surface of the water. Then we also measured the concentration of compound X in the water. And when we went out and did these measurements, we also measured all of these other important variables like the salinity of the water, temperature of the water and air, and wind speed. And we use several different techniques that I'm going to summarize quickly in the following slides. Here, these guys are extending a vial on the end of a pole down into the water to take a water sample. So we sampled the water whenever we went to do measurements and then sent those samples to the lab for analysis. What you can see in the background here is a flux chamber floating on the water, and I have better views of the chamber here. Essentially, what it is a dome that sits over the water and captures all of the fumes that come out of the surface. And as you can see, we can deploy it either over soil or water. Once again, we just capture the fumes, the VOCs, and then they run through tubing back to our truck for analysis. Another technique is known as open path Fourier transform infrared. Essentially, all that means is we have this device that shoots out an infrared beam down to a mirror and it reflects back. And based on the absorption of the infrared energy as it goes down and back, we can determine the compounds and their concentration in the air. What we try to do is measure the air both upwind and downwind, so that if the compound of interest is in the background, by measuring up and downwind, we can subtract out the background contribution. Another measurement technique we basically called passive air sampling. We have these canisters that are that contain a vacuum. You just open a valve, and so that the ambient air is drawn in passively. And then what we try to do is distribute enough of these canisters around the pond. I'll open them all up at the same time. And that way we measure the concentration of air, concentration of the compound, both upwind and downwind from the pond. Want to point out that the flux chamber that's sitting there capturing the vapors, it's giving us a direct measurement of the flux, of the amount of compound that's coming out. But the other techniques don't. They're measuring concentrations in the air, either upwind or downwind. So to convert those measurements into a estimate of the flux, we do what's called inverse modeling. Essentially, we construct them. We have a computer model of the pond. We assume a certain emission of compound X. And I'm just using this diagram to show to give an example of one of these models. So light pink is a really low concentration of the compound in the air, proceeding on to intense yellow, and that means a high concentration of that compound in the air. And then we use the model to predict concentrations at the sites of our canisters, these 4 squares, for example. And then we just have to adjust in the model, adjust the flux, the amount of compound coming out to get a good fit to the concentrations that we've measured. So that kind of a technique, inverse modeling, is used both for the canister measurements and for the infrared measurements. So at the end of the day, they really provide an indirect measurement of the flux coming out of the pond. But we always thought it was important to use different techniques so that one could help verify the other. So this slide is meant to give you an idea of what we actually measured in the ponds. So along this axis, I'm plotting the concentration in milligrams per liter. That's the concentration of the compound in the water. Notice that we have concentrations all the way from, this is 0.1 microgram per liter of water, all the way up to 1 gram of methanol per liter of water. So within the water, there are higher concentrations of these alcohols on average: methanol, isopropanol, ethanol, also methane, followed by BTEX, and then some of the other hydrocarbons are less, have a lower concentration. Whoops. So as you'd expect, well, here I'm plotting concentration along this axis, and then the flux along this axis of all of the different compounds and all of the different measurements that we took. And as you expect, there's a correlation. If the concentration of compound X is higher in the water, then there's more of it coming out into the air. I want to mention, we did not measure carbon dioxide in the water, but we did measure its flux. So we also know how much carbon dioxide is being produced by the ponds. To talk about some of the results, I want to put up this slide to define a few terms that we use. Typically in these facilities, there will be one pond that's receiving new water. As the trucks drive up, they'll get dumped into one pond. And then as those ponds fill up, the overflow will be pumped into auxiliary ponds adjacent to the first pond. So we speak, in the work we did, we talk about active ponds. Those are actively receiving water, new water, and the inactive ponds that only contain old water that's already been exposed for a long time. That said, I'd like to talk about just briefly some of the results that we found from this study. First of all, there are a lot more oxygenated compounds coming out of the ponds than are being added. The explanation for that, I think, is obvious. I mean, these compounds have been underground for millions of years. The first time they've ever seen a molecule of oxygen is when they come up to the surface, excuse me, and get dumped in the water. So while they're in the water, the hydrocarbons are being oxidized. It's being facilitated by microorganisms, and that's what produces the oxygenated compounds like carbon dioxide and alcohols and aldehydes. The other thing that we find, though, remember I talked about the difference between old water and new water. We found that the old water produces almost entirely carbon dioxide. And the newer water produces VOCs. The best explanation, I think, for that, in some ways this is a hypothesis, or we haven't really done the measurements that would demonstrate this, but I think the best explanation is that the ponds have a well-mixed surface layer. It's mixed by wind and wave action, and by the water as it enters, agitates the upper layer of the pond. But then there's a deeper layer that's stagnant. So when the water enters the well-mixed surface layer, those VOCs get churned out quickly in a matter of hours to days in the well-mixed surface layer. But others are able to diffuse into the deeper layers, and they stay there for a very long time. They stay there long enough to get oxidized to CO2. Another thing that we found is that alcohol, the dominant alcohol coming out is methanol, especially in the winter. But as I said, we're sure that's because the methanol is being added as an antifreeze, and it partitions to the water phase. Methanol and other alcohols are probably also oxidation, resulting from the oxidation of the hydrocarbons that go into the water. Carbon dioxide is the terminal. It's the end point of oxidation of these compounds. But if they're only partially oxidized, we can get things like alcohols or aldehydes, which all are found in the water. Okay, the big question: how much exactly is coming out of the ponds, and is it relevant to air quality in the Uinta Basin? This slide shows what happens when we extrapolated our results to all of the ponds in the Uinta Basin. We didn't do measurements at all of the ponds, so it did involve an extrapolation. But these are the results. Carbon dioxide is about 2/3 of all of the carbon compounds that are coming out of the water. Remember, I said there's no carbon dioxide going in. All of this CO2 is being produced by oxidation after the compounds wind up in the water. Another 1/4 are alcohols. A big part of that is the methanol that's being added that's present as an antifreeze. And then the remaining piece are the hydrocarbons that are coming out. I want to point out there's a margin of extrapolation error that we estimate to be pretty broad. I mean, unfortunately, this is not exactly an exact science, especially when we extrapolate. So basically what I'm saying is that we believe the true carbon dioxide emission is probably somewhere between 9,000 tons and 36,000 tons, minus 50 to plus 100. And this piece of the pie, about 1/3 of this pie, are VOCs that are entering the atmosphere. And so this slide shows the comparison of those VOCs, approximately 7,000 tons, compared to estimates of all of the other VOC emissions that are coming from all other sources. Our point being, as I said, we have pretty broad estimation bars or error bars on these numbers, but still our point is that about 9% of the VOCs that are being emitted by all sources in the Uinta Basin are coming from these ponds. Finally, I wanted to mention a work product that we developed in collaboration with the Wyoming Air Quality Division. We called it the Wyoming Pond Emissions Calculator. It's an Excel spreadsheet that we developed, like I said, under contract from WAQD. It's based on 2 literature models that gave the best representation of all of the data that we measured. So a user of this spreadsheet will input these quantities, and the output will be the total emission of that same compound from the water. The intention by WAQD is to require pond operators to measure all of these variables on some kind of routine basis, and then use this tool to estimate pond emissions. And it's not expected to depend on geography. These inputs, the most important input is just the concentration of the compound, as well as these other variables. So we expect that if anyone is interested, talk to Wyoming AQD, because we think the product will work in ponds in Utah and elsewhere. Well, okay, that's everything I had prepared for today. I want to put up this slide to thank the contributors, thank the other people who participated in this study. From our group, from GSI Environmental, and from the Wyoming Department of Environmental Quality. Like I said, that's everything I have. Thanks for giving me the opportunity to talk today, and I'll be happy to answer any questions that you might have.
Thank you so much, Mark. That was a very fascinating and insightful presentation. I know when I saw some of these same numbers from you, it's been probably a couple of months ago, it impressed me with the amount of VOCs that these ponds were responsible for. I would entertain questions. If you would entertain a couple of questions from the group today, I'd appreciate it. But one thing I wanted to point out, and John Rogers can verify this to me, that I think at our last inventory, we were showing that a great majority of the produced water in the Uinta Basin is going into deep well injection, and a smaller percentage is going to these ponds. John, is that correct? Is that what our numbers are showing us?
Yeah, we're showing about 95% of the water goes into class 2 injectional wells, with 5% the remainder in the ponds. And we're seeing a decrease in the amount of ponds obviously being permitted, and some are even being closed down. So that number is decreasing in the amount of ponds water taken.
So I think the important point from Mark's presentation is that even though there's a small percentage of the produced water actually going to these ponds, the ponds are a big contributor to the VOC profile in the Uinta Basin. And Mark, maybe my question to you is, how then do those VOCs become part of the ozone problem in the Uinta Basin?
Well, the ozone is occurring. Well, here's the basic science. Ozone precursors enter the atmosphere. There are 2 types. VOCs, or volatile organic compounds. Those are coming out of the ponds. The other type of precursors are the oxides of nitrogen, and they're being produced. Anytime you heat up the air, you heat up the nitrogen in the air. For example, in an internal combustion engine, then it oxidizes to form these nitrogen compounds, nitrogen oxides, or NOx, we call them. So it's the combination of the VOC compounds, the NOx compounds. When they get hit by sunlight, by ultraviolet radiation, then it kicks off a cascade of chemical reactions that produce the ozone. So the ozone is the problem. And ozone here is only a problem in the winter because, the inversions that occur in the winter trap those precursors close to the surface. For example, in the summertime, they mix out quickly and are distributed quickly and blow away. But in the winter, they get concentrated under the inversion layer. And there's enough ultraviolet radiation coming from the sun and reflecting off the snow, that it's able to kick off these photochemical reactions that produce ozone. So long story short, the VOCs coming from the ponds are ozone precursors. And that's how they contribute to the winter ozone problem.
Thank you for that explanation. Are there a couple of questions from the group that could be directed to Mark at this point?
I have a quick one. How does this, how do these reports affect us in the basin who have ponds in terms of long-term strategy and, you know, what trickle effects it'll have on us with the state?
I'm not sure I can answer that. We just feel like we're the messengers, and it's up to the state or the tribe or EPA to decide how to regulate things going forward.
John,
I
do
see
you know?
that, well, that's a good question. I know from our point of view, we haven't addressed how to regulate these ponds in terms of air quality. I think that we would want to work collaboratively with the Division of Air Quality and determine what is the best course of action there. But I don't know that we've established any clear policy on what should be done about it. At this point, we've focused on the ponds from the standpoint of leakage and water quality, but we haven't done much in terms of air quality.
Okay, thank you.
I see Ricky Ranko Browning has her hand up. Ricky, did you want to make a comment at this point?
I can comment to Kristen's question unless someone from DAQ wants to jump in and have a better response than what I'm going to have. But I did also have a question. So Kristen, my understanding to that would be as we move through the non-attainment process and the state puts forward a SIP and EPA puts forward their kind of counterpart to that for the federal areas or the tribal areas where they have jurisdiction, they're going to have to provide and demonstrate a 15% reduction in VOCs. And so I would anticipate that if what we're saying here is that 9% of the VOC emissions in the basin are coming from this 5% of water roughly going into produced ponds, that's likely to be an area, I would presume, and DAQ can certainly correct me if I'm wrong, but I would presume that DAQ would be looking at those ponds as part of where to find a 15% reduction in VOCs. The question that I have is, where are most of those ponds located? Are they within the state jurisdiction or within EPA's jurisdiction?
Hi, Ricky. This is Lexi. The jurisdiction question is always tricky because it's highly contested. The maps that DAQ and our attorneys have given us indicate that we have some ponds under state jurisdiction, but more ponds under tribal jurisdiction and EPA's jurisdiction.
Thanks, Lexi.
And this is Greg, as far as Martinson with DAQ, as far as, going forward on the SIP, pretty much everything's in the mix. They're going to, as that goes through modeling and the permit folks come in, they'll have to evaluate where we're going to look for that 15% reduction. So there's no guarantee it'll be 100% ponds. And obviously that's going to be the process is still kind of a starting stage. And since there's multi-jurisdictions in this, it's going to have to be a coordinated effort. So, obviously we'll look at ponds, but we'll look at pretty much everything out there and see what makes the most sense. And hopefully, with the least economic impact, we're hoping for some low-hanging fruit we can get out there, but right now we're not sure where that's at definitively at this point.
We do have one more raised hand from Tara Gross. And just to remind you, when you raise your hand, you will have to manually lower your hand once your question's answered. But Tara, do you want to go ahead and ask your question.
Yeah, hi, John. I was just curious on the water in those ponds. Are they mixed formations? Were they coming from different formations within the drilling? I was just kind of trying to think about the water. I know each formation has its own water quality, and how much of that was, in the pond. Was it multiple frac jobs? Stuff like that. I was just a little curious.
I can tell you what I know, and maybe either Bart Kittle or John Rogers could chime in, but I understand that there's not a real good tracking of where the water comes from. A lot of it is produced water that comes up along with either oil or gas production. And because there's so much of it, there's not a lot of infrastructure in terms of deep well injection to put those conveniently into. Some of it could be flow back from hydraulic fracturing stimulations, but for the most part, my understanding it is coming from actual production, and it's mixed. It could be coming from anywhere. Is that what you understand, John?
Yeah, I mean, the only ones that you'd really know where it's coming from would be if it was a facility for a particular operator. It wasn't a commercial facility, so you knew where it came from. But these others take product from all over.
Yeah, I mean, my feeling is it's driven by the economics. If you have a load of water in your truck, you're going to take it to the closest pond that offers you the best deal.
Yeah, that's correct. Generally speaking, if you look at the geography of where the pond's located, that's whatever the producing formation that's closest to it would most likely dominate the water input, but there could be other variables.
Well, I think we need to move on with our presentations. Mark, thank you so much. That was well presented, and appreciate you answering a couple of questions also there.
Thank you.
As we continue in our discussion of produced water, Mark has pointed out the potential air impacts of these evaporative pits, and obviously produced water comes from a lot of different sources out in the Uinta Basin. But the next question we would have is there something else we can do with produced water other than either disposing it by injection or putting it into these evaporative ponds? So the next presentation comes from an outgrowth of an effort by the Groundwater Protection Council. And you'll hear more about who they are and what they are. But Utah is a member association or a member state to that association. And it includes multiple state agencies, both in the oil and gas regulatory space and in the water regulatory space. Utah has been a member of the organization for a long time. I have been a representative for the state for a few years now, and about 2.5 years ago, I was encouraged to participate in a study of produced water, which the Groundwater Protection Council produced in June of 2019. So you're going to hear now from Mike Nicholas, who is a special projects director for the Groundwater Protection Council, about that report and GWPC's interest in studying produced water. So let me introduce Mike. Mike received his bachelor's degree in geology from Indiana University, has been a licensed professional geologist since 1986, and he's also a member of SPE. He's been a special project director for GWPC since May of 2005. In this capacity, he's responsible for development and management of projects related to water and energy issues and underground injection control. I met Mike in the early 2000s when he had his role similar to mine in the state of Indiana for the Indiana Division of Oil and Gas. He spent 20 years there and 2 years as the state director of oil and gas for the state of Indiana. So Mike, we'll go ahead and turn time over to you to talk about GWPC.
Thank you very much, John. The first thing I would like to do is I would like to invite our members from the Groundwater Protection Council staff. I'd like to introduce them. You've already heard from one of them, Tara Gross. She submitted a question. Tara is our senior geologist and water management specialist. Mark Lane is on the call. He is the technical director for GWPC. He's a licensed professional engineer. And we also have Dan Yates, who's our associate executive director. And finally, our executive director, Mike Paik. And I'd like to ask Mike if he would like to say anything at this time.
Mike, can you hear me? Yeah, I guess you can.
Yeah.
I'll be brief. First of all, I want to compliment the entire Utah staff and the folks on the call. This is a topic that hasn't been discussed widely across the United States in the context of oil and gas. And I think that the fact that Utah and the division and Wyoming also are talking about it is quite significant. And it's taken work, and something that conversation will continue. And I can only compliment you all for talking about the topic and looking for alternatives if there are any that are economically viable. So compliments certainly from me. John Baza did mention that he has a long-time affiliation with GWPC, and as does John Rogers, who's on the call and introduced the topic, and more recently Bart Kettle, who I'm looking at, Bart down in the corner of my screen. Bart's been real active in the GWPC from the division on some of the data things that we're doing. And then historically, Dan Jarvis, who spent a long career with the division and now is actually working for the Groundwater Protection Council. So we go back a long, long way with the division. John did tell you that he was a member of the board of directors of the Groundwater Protection Council. And I might also add that John is a member of the executive committee of the Groundwater Protection Council, which is the officers of the association. So he's rightfully claims a long history and a little bit demure on how important a role he plays in the organization. The produced water effort, as John pointed out, was begun by a board resolution, and I think that was significant. The board of directors of the state oil and gas agencies that are members of the board and the water agencies that are member of the board identified produced water as a key topic and passed a resolution that culminated in the report that you're about to hear some details from Mike Nicholas. But the GWPC's effort continues through a produced water task force, which John Baza and Shelley Chard, who's the water division director in Oklahoma, continue on. And there are a number of projects that they're working on that I won't go into this morning. But I will tell you that come September of this year, the last week of it, we hope to have the Groundwater Protection Council's annual meeting in Salt Lake City. We're expecting to have it. We had to postpone that meeting from this last September. And I think it's reasonable. Let's all knock on wood here. I think it's reasonable to expect that the Groundwater Protection Council will have a large meeting, annual meeting in Salt Lake City the last week of September of this year. And germane to this conversation today is produced water will be a big part of that agenda. So I encourage persons that are on this call to kind of keep a heads up or if you're not readily exposed to GWPC activities and meetings and that sort of stuff, to go to our website and express your interest in being contacted routinely. So more to come on the topic. And with that, let me turn it back over to Mike Nicholas.
Thank you, Mr. Paik. Appreciate that. And for those of you who can see the screens. I'm going to now attempt to put my presentation up. Hold on just a moment. Wait a minute. It'll take me a second to get this right because every time I do this, it turns it sideways. So I have to fix it. Okay. Can everybody see the presentation now? Good. I'm glad to hear that. As John said, my name is Mike Nicholas. I've been with GWPC since 2005, and before that with the Indiana Division of Oil and Gas for 20 years. And this effort, this produced water report, we consider probably the seminal report on produced water for a couple of reasons. The primary reason being that we tried to cover the three main areas related to produced water. That is, the areas of regulation, the areas of use in oil and gas, and the areas of use outside of oil and gas. So who are we at the GWPC? Obviously, we're based in Oklahoma City. We're the National Association of State Underground Injection Control and Groundwater Protection Agencies. And we really are guided by our mission, which says we want to protect and conserve groundwater for all beneficial uses. And that includes produced water, because we recognize that groundwater is a critical component of the ecosystem. We don't think of groundwater as just groundwater anymore. It's part of a larger package, groundwater surface water interaction. So we are concerned with all water, truly. We provide important forums. Mike mentioned one, our September meeting coming up here, where we get stakeholder communication. We do research, the Research and Education Foundation. And the purpose of all this is to help governmental agencies in the protection and conservation of groundwater. So we had many study partners, 4 primary study partners for this work. They included the Department of Energy, American Petroleum Institute, our Research and Education Foundation, and the Environmental Defense Fund. So there were something on the order of 100 plus authors of this report, with John Baza and Shelley Shard being our report leaders, in effect. And we decided in the end to organize this report around 8 principal areas. First, of course, table of contents, preface. The executive summary picks up all the pieces from the introduction and the modules and puts them in a shorter version for people to read. But we decided on what we call this modular approach. And the modules are guided around 3 basic principles. The first of these is, what are the legal and regulatory frameworks? How is oil and gas produced water regulated? The second is, how is oil and gas produced water used or reused inside the oil field? And finally, how is it used, or how can it be used outside the oil field? So what were our goals for the report? One of the critical goals was to provide information to the public about produced water and how it could be used. We wanted to encourage the oil and gas industry and the state and federal agencies to gather more data about produced water, so that would facilitate additional reuse. And it would also inform more research into the topic. But our primary goal was to expand the use of produced water in a manner that could be protective of the environment and public health. So what's really driving this conversation about use of produced water, reuse of produced water? Well, there are almost 1 million producing oil and gas wells in the U.S., and these generate 21.2 billion barrels of produced water per year. That's a lot of water. And there's a lot of freshwater stress that's driven by rising populations and regional droughts. And we all know we're in approximately the 100th year of a 300-year drought cycle. So we can expect these drought events to continue for some time to come. Now, while the volume of produced water is relatively small compared to total daily use, its availability can be significant on a local basis. So how is produced water managed right now? Well, as Mark said, a lot of it is reinjected. Nationally, we're looking at about 85% of water being reinjected, 45% of that for enhanced oil recovery, and 39% for just disposal. There's also a little over 5% that is surface discharge at this time, and about 3.4% nationally that is put in the evaporation ponds that Mark was discussing. We also have not almost 7% that's managed by offsite commercial disposal. But as you see at the top, we have I'll call it a paltry 0.6% that is used in non-oil and gas areas. So we really feel there are good opportunities for expanding the reuse of produced water, both inside and outside of oil and gas operations. But there are challenges inside and outside. The economics plays a huge part in whether you will be able to reuse produced water. Transportation, the most costly element in moving water around, is a big part because it concerns the costs and it concerns the risks associated with spills, and et cetera. And of course, treatment technologies are a big deal. There's a lot of research going on in treatment technologies. So let's talk for a few minutes about the individual modules that we developed for this report. The first talks about regulatory and legal frameworks. Now, while the EPA has regulatory authority for NPDES in many areas and also under the Resource Conservation and Recovery Act, it's primarily the state's responsibility to regulate oil and gas activity, especially upstream. For this report, we contracted to have law students from Tulane University do research into regulatory management, and we picked 6 states to do this. We decided to pick the states from different regions to do this. And as you can see here, what we tried to point out was that the regulatory picture is not as simple as some people would want to believe. New Mexico is a great example of that. The New Mexico Oil Conservation Division regulates underground injection control, but land application of produced water is regulated by their Department of Transportation, and water discharge under NPDES is regulated by the EPA. This we found in many of these 6 states. There's variability, and we expect that this variability would carry over to many other states. So what about water rights and responsibilities? Are those as variable as the regulatory elements? Because produced water is subject to state water rights laws. In many states, produced water is considered groundwater, and that's a proprietary item. The legal frameworks also vary by state, and it's really necessary for you to identify who owns the water, because understanding the changes in ownership is going to allow you to understand the differences that are based on local state laws and regulations. And what about the role of water and mineral rights and surface ownership, which is critical to addressing how and when there might be compensation for or liability related to beneficial use of produced water? So we also looked at the water rights ownership and produced water liability in the same 6 states. And again, what we saw was a mix. New Mexico is a prior appropriation state, which means that the landowner owns the water. And this includes produced water. Now, New Mexico recently passed a new statute regarding produced water, which I won't go into in specifics, but it would change this picture somewhat. But even though the landowner owned the water at the time of this report, the operator still had some produced water liability. Other states have different sections of water responsibility. Reasonable use, what that means is that while the landowner may own the water, other people can apply to use that water and may have to be allowed to use it. We think it's very important for states to consider produced water as part of their state water planning process. We think it would facilitate more reuse. So state water planning is very important to states, as more regions are experiencing these water shortages, including Utah. But only 3 of the 6 states we took a look at for our legal research, include produced water as a component of their water plans. But as treatment technology advances and populations grow and water scarcities are more pronounced, we think the produced water is going to be looked at as a resource that could add to the state's water balance sheet. A good example of this is the Oklahoma Water for 2060 plan. It was developed using 13 geographic regions, and its goal was to demonstrate how the state could use the same amount of water in 2060 that it used in 2010. And it included all water resources that they could find, such as brackish water, produced water, reclaimed water from municipal industrial processes and others. And it also included conservation measures and methods as a principal element of the water plan. So what did we look at in Module 1? What did we talk about? Well, we found first that states regulate oil and gas activity. That's a principal element. But water rights and responsibilities vary from state to state. Considering produced water during state water planning is a critical element of how we're going to get to more produced water use. But regulatory frameworks are going to evolve to facilitate reuse, especially when we talk about reuse outside of oil and gas operations. So let's talk about use inside oil and gas operations for a minute. There are several opportunities for beneficial reuse. It can be used beneficially, of course, in conventional production for enhanced oil recovery. And also it can be reused in drilling and hydraulic fracturing for unconventional resources. There are many benefits to the reuse of produced water. A principal benefit, because of droughts and other things, is to reduce freshwater usage, which could benefit local water needs. It can also minimize produced water disposal, which can be costly and which has problems nowadays related to the capacity limitations on formations, because there are a number of formations that are becoming overpressured and may have limitations on injection. It can lessen the potential for induced seismicity in some areas from injection. The GWPC, in concert with the IRGCC and what we call our state regulatory exchange, has recently completed our 2020 update to our induced seismicity guide, which covers a lot of areas related to injection and or hydraulic fracturing. But we can also reduce the costs and risks associated with transportation. So that's another benefit of reuse inside the oil field, because there's less transportation, lowered costs. And that is the key. Cost is a key driver in produced water management and reuse in oil and gas operations. Based on the economics of reuse that we developed here, you can see there is a dropped step in water cost with reuse versus water costs without reuse, which will lower the total water costs. So what are the challenges of using produced water? There are several of them. First off, you have to adapt to the state regulatory frameworks. As they change, adapting to them changes. Transportation is a big issue. Transportation is the most expensive issue related to the movement of produced water, and it's also a risky proposition when it comes to the potential for leakage. Storage is also an issue. In some states, pits are not allowed. In some states, tanks must be used. In other states, pits have to be lined. In some states, they have to be double lined with leak detection between the liners. Underground injection can be a challenge, especially in areas where there are minimal numbers of formations. Pennsylvania is a good example of that. Pennsylvania only has, at last count, 8 underground injection control wells in the Class 2 program for injection. Treatment is a challenge because there are a lot of things in produced water that we're not absolutely sure of, because there are few analytical methods that can detect them. And that means that treatment has to be established that will treat groups of compounds so that you can remove these. Spill management and mitigation. The spills of produced water are very hard to manage. There are techniques you must follow in certain orders to properly mitigate spills. What are you going to do with the treatment residuals? There are always going to be high density treatment residuals from these treatment processes. In some cases, there are compounds that are useful and can be sold. In other cases, you're going to have to dispose of these treatment residuals. And how are you going to do that? Mark talked about air emissions. That is clearly a challenge in the Uinta Basin, and it is a challenge elsewhere. And finally, you have to protect wildlife. When you talk about pits, we're talking about fencing around pits or netting over pits. One of the things we found in this area was that there's a midstream growth potential. Midstream companies are coming in and they are managing water. That is their business model, is to manage water. And in some cases, actual operators are cooperating with other operators in multi-company sharing of water management systems. There's some positives and some negatives to this. The positives are that this can reduce overall costs because of the economies of scale when you're talking about a single facility that takes water from a lot of different production operations. In doing that, you reduce the upfront capital costs for developing these systems, which allows producers to focus on high return completions and productions rather than managing water. And it allows a better overall water balance in the supply and demand structure. What are some of the negatives, though? Well, if you're an operator and you've given your water over to another company to manage, you've lost absolute control of that water in that system. However, you may still maintain some liability, so there is risk involved there. There's a commitment needed to build, for mainstream to build systems. In other words, they're going to have to know that they're going to get water and certain amounts of water from certain sources over long periods of time in order for them to commit capital resources to build the systems. There are water mixing problems. If you're mixing water from different sources, in some cases, in produced water, you can get precipitation, which could include naturally occurring radioactive materials. So you have to be careful about that. So a key point here is there are additional research needs and policy initiatives that have to be addressed to help facilitate more use of produced water in oil and gas operations. Some of this research needed includes leak detection systems, the water treatment systems, improvement of enhanced evaporation or desalination if it can be done effectively and safely, some automation in treatment systems to lower costs, separation of saleable products like iodide from during the treatment process. What are the water treatment research needs? What new research treatment technologies are available to manage this water in a way that's going to make it usable? And of course, there are regulatory changes that may be needed to facilitate discharge. When we looked at use inside oil and gas, we primarily looked at 7 different basins. And these basins were all large, unconventional production basins in effect. The Appalachian Basin covers parts of Ohio and New York, a large part of Pennsylvania, and almost the entire state of West Virginia. The Niobrara is principally located in Colorado, but it is located in other states such as Nebraska. The Bakken is primarily in North Dakota. Central Oklahoma Basin, of course, is in Oklahoma. The Permian Basin is in New Mexico and mostly in West Texas. And then we also looked at the Eagle Ford in Texas and the Haynesville, which is in Texas and Louisiana. But what we found is that reuse varies by region or area, and it varies significantly. The national average is about 10% overall reuse inside oil and gas and elsewhere. It varies from 0 to 67% across the 7 basins. If you look at the Eagle Ford on this chart, you see there's very little reuse. Now, the Eagle Ford produces very little water, so there's less need for reuse. But in the Appalachian Basin, it's about 67%. Now, there are reasons for that. Most of the Appalachian Basin production is in Pennsylvania. And as I mentioned earlier, Pennsylvania only has 8 injection wells. So that water has to either be taken somewhere else, mostly it goes to Ohio when this happens, or it has to be reused in the region. So Appalachia has a large reuse component. So let's take a look at what did we talk about in Module 2? Well, first off, we found that cost was the key driver of reuse. if reuse is not economically feasible as related to injection, then people are going to inject their produced water. But as reuse costs come down on a per barrel basis from treatment, transportation, and other factors, it's going to become financially feasible to reuse more water in the oil and gas field. There are challenges and opportunities that affect reuse in oil and gas. We talked about some of these challenges, including the air emissions, wildlife protection, spill management, and so forth. We found that produced water midstream is a growing thing. It's emerging as a water management strategy, and it has positives and it has negatives. We also noted that there are a number of research needs and policy initiatives that have to be addressed to expand produced water reuse. And of course, we found that reuse varies significantly by region and area. Now let's talk about Module 3. This is the module where we talk about how can produced water be used outside of oil and gas, and what are the research needs that we have in order to do that? We consider Module 3 our forward-looking and most challenging aspect of this report. Although some small-scale efforts exist, states like California have some irrigation use of produced water in some areas, for example. In order to move forward with more reuse outside of oil and gas, we're going to have to go forward with some caution because the research needs need to be taken up in all areas, including the environmental impacts of produced water. Current reuse, as I mentioned, is less than 1% outside of oil and gas, at 0.6%. Some use in irrigation for crops and for non-crops, and some stream augmentation and others. But in order to use produced water outside of oil and gas, we have to understand that potential risks have to be appropriately managed. We've got to prevent unintended consequences from the use of this produced water outside oil and gas. And there are several primary reasons for that. First is what's in produced water. There are a lot of mineral salts. The total dissolved solids, cations and anions, can be very high. In some places, for example, in Michigan, some produced waters are between 200,000 and 300,000 parts per million, extremely high total dissolved solids. There are organic compounds in produced water. Mark mentioned several of these, BTEX, other volatile organic compounds. There are inorganic metals, such as arsenic and others. And there are other inorganic constituents like sulfates and ammonia. Naturally occurring radioactive material can be a problem, especially when we're talking about the mixing of produced waters and precipitation of norm. And when you talk about using produced water in hydraulic fracturing, what's going to happen is the water that comes out after that, the flow back, is going to have chemical additives in it. In addition to that, when you put these chemical additives downhole into geologic formations and they interact with the groundwater that's in those formations, you're going to get transformational byproducts, other products that come out that you did not put in. So how do you deal with all of this with respect to using produced water outside of oil and gas? Well, we came up with a basic decision-making framework to allow people to assess the feasibility of using produced water. Now, this is a simplified version of it. In the report, you'll see a much more complex version. But the first phase in this is to take a look at the program itself and determine whether or not you think it's even feasible to move forward. If it's going to be too costly, then you're probably not going to move into phase 2. But if you do move into phase 2, what you're going to do there is you're going to identify the stressors of interest, these constituents of concern that are in produced water, and you're going to assess the risk of those constituents on things like crops and livestock and even humans. After that, you're going to move into the risk assessment as it relates to the treated produced water. In phase 2, you were looking at the raw produced water. In phase 3, you're looking at the same thing essentially, but you're looking at it from the standpoint of what's the produced water look like now after it's been treated. And finally, you're going to go to phase 4, where you're going to assess risk management. What things can you do to mitigate any problems that may occur in the use of this produced water? And from our standpoint, the level of treatment and research needed depends almost entirely on how you're going to use the water. We call this the fit for purpose model. That's been used by many other people. So we just kind of glommed onto it and said, that's a good way to look at this. If you're looking at it from the standpoint of use in the oil field, you're looking at far less treatment, far lower costs for transportation and other things. What about if you're going to use it in irrigation or agriculture? Well, if there's nearby agriculture, the transportation costs may be low. But of course, the treatment you're going to have to do to make it usable for crops is much more intense than what you'll get in oil and gas use. And finally, if you're going to use it for a public water supply, for drinking water, you're stepping up your game significantly from even the use in irrigation. And the use in, it's my opinion that the use of produced water for drinking water purposes in most all cases is fairly far into the future. When we looked at all these things, we found that there is a lot of published literature out there on produced water, and that family of research is growing. However, there's a lot more research that's needed. Identifying reuse options and current or emerging needs or drivers in specific regions is a big deal. We have to continue to evaluate the legal and regulatory questions because those change over time, especially as it relates to things like public perception. How is the public going to view the use of this produced water outside of oil and gas? Are they going to be kind of questioning whether or not it's safe to use it? Are they going to accept it because droughts are telling them that they have a real need for fresh water or more water? And then what about expanding our knowledge and tools for characterizing treatment, risk assessment, and reuse? The best one I see here is number 1, the analytical methods for characterization of produced water. When you are trying to analyze the constituents in produced water, you could be talking about water that has high salinity contents. You have to dilute that water significantly to get readings on a lot of these compounds that are in produced water. And there are a lot of compounds and a lot of elements in produced water for which there are no analytical methods. That's why we have to look at treatment technologies, because the treatment technologies have to be able to deal with large swaths of these chemicals. They have to be able to get rid of a lot of chemicals, not just one specific chemical. So what did we learn overall in Module 3? Well, current reuse right now is kind of minimal, but there are opportunities for reuse outside of oil and gas. We have to understand the potential risks to make sure there aren't any unintended consequences from using it. We have a 4-phase decision-making framework that allows us to evaluate and manage these risks for the reuse. And the level of treatment and reuse research depends almost entirely on how you're going to use it, that fit-for-purpose model. There are lots of practical issues, including how does the public perceive this? What are the economics? What are the logistics of moving water around? And what about the regulation? Is it changing? And what are the benefits for doing it? We note that public literature is there and growing, but we need more research to assure reuse can be done safely and effectively. In the end, it comes down to this. Produced water really has local potential. If you've got a produced water source and you've got the treatment technology and you have the need for water in a local area, it can be very effective, efficient, and cost efficient. And it can offset freshwater use. However, the use of produced water outside of oil and gas requires very careful thought. At that, I'll be happy to answer any questions.
Mike, thanks a lot. I totally appreciate your efforts in putting that presentations on. One question that I had for you, I know that even during the pandemic, the task force was trying to advance the cause of produced water and the research needed. We had a virtual event last summer with New Mexico and New Mexico State University. It was my impression that the state of New Mexico has been able to advance the cause to a great degree, both in terms of their legislation, their study of produced water. Can you briefly talk about what GWPC is doing with the state of New Mexico right now to move the needle on this?
Well, I tell you what, to be perfectly honest, John, I think if Mike Pake is on the call, I think he might be better able to answer that question. Mike, are you still there?
Yeah, I am. And let me just ask, Mark Lane, are you still on?
Yes, I am.
Okay. So I'm going to, John, just briefly say that we have entered into a memorandum of understanding with New Mexico State University and the Groundwater Protection Council to help New Mexico advance its precursor work, if I can call it that, for using produced water. They take it very serious in New Mexico. They're not actively using any large amounts of it at the time, but we do have a project that'll enable them to make better decisions. And Mark, if in 1 minute you could describe that would be helpful, perhaps.
What we're looking to do is to take all of the disparate data systems and data we're able to gather from water, produced water, and data quality that they've collected up from contributions from industry and other efforts over time, and map that into a GIS analysis dashboard so that a user can come in for their particular area and try to determine what quality of water and quantity of water may be available for them to use. That's the quick overview.
Is that helpful, John, for now?
Yeah, I just wanted to make sure we mention New Mexico, because if Utah moves along this path and we start looking at how we want to use produced water, we've got a neighboring state, even though we touch at one point, that has really done a lot of work to address produced water, especially out of the Permian Basin where they've had the big increase. So I think we could use that as somewhat of a template in the state of Utah to say, well, how are we going to look at produced water here? So thank you for saying that.
Fine.
We had one chat box comment came through asking whether the presentations would be available. I know from the groundwater protection standpoint, we have no problem in putting the presentation as part of our collaborative meeting materials. Mark Mansfield, you'll have to let us know whether your presentation can be made publicly available or is publicly available. The other thing I would say is that we have been recording this entire event, and for those who want to review the material afterwards, we can take a look at it that way too. And Mark indicates that yes, he's going to send us his presentation. Are there any other questions or comments? And if not, I'm going to turn it back to John Rogers for a quick wrap up. I know that we're almost out of time here, but thanks to our presenters, and all of you have stayed on for this discussion. John, back to you.
Thank you, John. Appreciate that. Appreciate Mark with his USU group and Mike with GWPC and our technical staff to get this up and running. I thought it went very smoothly. As the name indicates, collaborative means it's the opportunity for us to share ideas and talk to one another. Right now, I'm looking, we have 82 people online. So I'd like to take the next few minutes to have anyone that have comments for either state agencies or federal agencies. I usually start with the counties. Duchesne, are you out there somewhere? Anyone gonna hop up and speak for Duchesne? How about Uinta County? No takers, huh? Okay. Well, anyone out there would like to have some issues that I'd like to bring up with some of the people online here? It's a good opportunity to meet and discuss things. It's a little easier when we're in person, but this is the opportunity if you would like to take any time.
Hi, John. This is Seth Lyman at USU.
Yes, Seth.
I just want to remind folks it's the winter ozone season, so reduce emissions if you can, or to the extent you can, to help us get through the winter. We have snow on the ground, inversions, so it's that time of year.
Yeah, good reminder, Seth.
John, this is Bill James with Utah Division of Wildlife Resources. I'll just offer that there is interest if oil, gas, and
You're breaking up, Bill.
Yeah, I'm sorry, I don't know what my problem is. I just wanted to offer that we, the Division of Wildlife Resources, are willing and interested in a panel that might take a look at issues associated.
Is everyone else having a hard time hearing Bill?
Yeah, I can't hear anything.
No, I can't either, John.
Sorry, Bill. Okay. Well, with that, we'd like to again thank everyone involved here. Our next meeting will be April 8th. And if anybody's guessed where that'll be, online, or maybe things will improve, we'll see. But anyway, mark that date down, April 8th, for our next collaborative. So thank you all and appreciate you. Stay safe.